All right, hey, what's up, guys? All right, so I hope you guys got a chance to look at this. Um, and I apologize for pushing the session back. Something came up. Um, all right, cool. So first question, uh, the same one you guys have been seeing. All the reagents you would need to make this ether, right? So remember, we need three things. And so what were those three things that we needed? Anyone remember? Yeah, exactly. You need alcohol, you need alkyl halide, and then you need a base, right? And so remember with Williamson ether, both of these components, this component and what color? I guess this component, they both come from either the alcohol or the alkyl halide, right? And so in this case, which portion is going to come from, let's say, the alkyl halide? The yellow portion or the brown portion? Yeah, the brown, right? Remember when it's an ether, what you want is you want the alkyl halide to be coming from the least sterically hindered portion because this is going through SN2. And so that's that, right? That means this other portion is the alcohol. So you have that. And then in order for these to react, you need to make this a good nucleophile. The way you do that, you add in a strong base. And so someone give me a strong base. Anyone? A strong base that's strong enough to deprotonate this guy. No one? No, not ACL. ACL would be an acid. No? Oh, NaOH. Yeah, let's do NaH. I think NaOH would be a little bit. It wouldn't be. Oh wait, hold up. I think NaH would be better, just because it's. If you did NaOH, the pK difference wouldn't be a lot, whereas NaH, the pK difference is vast, right? Because this is 16, it's 35. So this base is like a hell of a lot stronger than NaOH. Okay, so yeah, this works. Okay, any questions? Cool. All right, so missing reagents, right? There may be more than one answer, so whatever I put or whatever you guys choose, there may be other possibilities. Okay, so here, right, we're going from an epoxide to this, right? This has a specific name. You guys remember what this was called? It's a very specific name, like the type of group. Close, Owen. Yeah, so it's a diol, right? So diol means two alcohols. And so look at their stereochem. Are they cis? Are they trans? Right. So this would be trans diol. Okay. So from looking at this, right, which side of the epoxide did we attack? Did we attack the more subbed or the least subbed? Right, we attack the least subbed, right? Because remember the epoxide ring is on a dash. And so you look for, well, which one of these OHs is a dash? Because that means this oxygen atom came from the epoxide, right? So if this side is still a dash, that means we did the attack from the opposite side. And so since we're attacking the lead sub, what conditions are we in? Yeah, we're in basic. Nice. Right, so we're in basic conditions, so we got that. And so now we just got to figure out, well, what are we actually using? Anyone know what we're going to use to make this? Not NABR, right? Because we're adding an OH. Now, yeah, nice. Right, so we're adding OH, so pick your metal. So I'll just do generic NaOH. So 1 NaOH, 2 what? What do you follow that up with? Yeah, water, right? Because you need to provide some proton source for this guy to get the hydrogen on there. Okay. Does that make sense on why we did this? Any questions about this one? Pyridine. No, you can't do pyridine with this. What are you specifically at? Yeah, pyridine's a base. So yeah, it is a base, but then remember we're adding on an OH, so we need something like our nucleophile has to have some OH component, right? So that's where the NaOH comes from, right? Cool. What about here? Next one. What do you guys say? Yeah, HBr, right? So it's clear that remember there's a shift, right? Because look, the OH was right here, and now the Br is in a whole different position. So we had some rearrangement, right? And so you have to think about your reactions that have a rearrangement component. And so we know what, if you want to turn ROH to RBr, right? We have two choices. We have HBr, right? And in this case, what is HBr going to do? Is it going to do SN1 or SN2? Yeah, we need SN1, right? Because we had rearrangement. We cannot do this. We cannot do PBr3Y. Why couldn't we use PBr3? Exactly, yeah. PBr3 forces SN2. Okay. So in this case, if we use HBr, we will get SN1 because it's a secondary alcohol. And that's what we want. We want SN1 so we could get rearrangement. Okay. Questions about this? Secondary here. Okay. Cool. What about here? What do you guys want to do here? Start with NaH. Yeah, exactly right. So this is kind of like a Williamson ether, but in this case, it's sulfide, right? And so what are we doing? We're adding a methyl group on here. And we know that if we want to like add an R group, we want to make this guy nucleophilic. And so basically we start with some base, right? So let's do NaH. And so what is that going to do? That is going to deprotonate this proton on here. And so after NaH, we get S minus, right? So now we have a good nucleophile. And so remember, we're adding on a methyl group. And so what do we follow that up with? So 2. What do we add? Yeah, exactly right. So CH3 and then some Lg. So let's do Br, right? And so this makes sense, right? Because if we react this with methyl bromide, we'll just have a simple SN2, just like that. Okay. Questions about these? SN2, the last one. Yeah, yeah. So this is going to follow an SN2 mechanism. Okay. All right. So which one of these is going to undergo rearrangement, right? So let's go through each one individually. Is this one going to undergo rearrangement? It is. It is not. Right. This one can't undergo rearrangement. Okay. So look, right. So we have a secondary carbocation, and so you look to its only to its adjacent partners. If it's more substituted than the carbocation we're at, then we will do rearrangement. So if we go here, this is primary. So it's less substituted. So no rearrangement. This is secondary. It's the same, right? So no rearrangement. Yeah, exactly. Immediate neighbors. We wouldn't look all the way over here because that's too far, right? So this is a no. Wow, that was bad. No, right? What about here? Yeah, here we would, right? So if we look to the left, this is primary, so it's not going to happen. But here, yeah, exactly, we would have methyl shift, right? Secondary next to quaternary. So yes, it will undergo rearrangements. What about here?
No.
Yeah, exactly, no. So same reason, right? So immediate neighbors, this is tertiary, so we need something that's more than that. And even if, so let's do this. We need something that's more than that, right? So secondary, that's not more. Primary, that's not more. Tertiary, that's not more. And even if, let's say this was quaternary, would this undergo rearrangement? Then now this molecule. This would not, right? Because what if we move this methyl over here, what do we just make? We just made a tertiary carbocation, right? So tertiary carbocations do not undergo rearrangement as far as methyl shifts and hydride shifts are concerned. Okay, so this is a no. All right, what about this one? Yeah, this one can, right? Because you can resonate. You can resonate this pi bond over here, right? And then you will have you have a carbocation here. And so this is rearrangement, right? As far as stability, they're the same stability, but it doesn't follow the same. Yeah, exactly. That's why it's a little confusing here. So I guess there's two different types of rearrangements. Here, the main stabilizing effect why we're doing hydride shifts and methyl shifts is because of hyperconjugation, right? Here, this is a totally different stabilizing effect. It's resonance. And so I guess it follows a different rule, even though we're forming like the same carbocation, it's secondary, and this is secondary, it would still undergo rearrangement. I don't know if I could provide a better answer than that. So let's just do this. If a carbocation is allylic, in this case it is allylic, it's going to undergo rearrangement. Okay. We good with this question?
Yes.
Okay, cool. All right, so everyone's favorite, right? All right, well, let's walk through this mechanism, okay? What's the first step?
Protonate.
Yeah, nice. You're gonna protonate. And so you get this, right? Exactly, yeah. And so after that you made a good leaving group, and so it's gonna leave, right? So let me copy and paste. Oh wow. My bad, guys. I'm super slow at this. Okay. What the fuck? Okay. All right. So now you have a carbocation here, right? What's gonna happen next?
Start counting from the carbocation.
Right. And so in this case, it's a little tricky, right? Because what we have here is we have to figure out which bond we're actually breaking. Okay. So what I'm gonna do, I'm gonna do both ways because it's trial and error, right? It's trial and error. So I'm gonna do both ways. And so what do I mean, right? Well, we need to figure out if this bond is breaking or if this bond is breaking, right? And so what do I do, right? You start counting. You start counting from the carbocation and you stop counting out wherever you stop counting, right? So 1, 2, 3. And so notice here we reached the intersection, right? In this scenario, I'm breaking this bond. So I'm not going to count this way because this bond is breaking. I need to count in a continuous fashion. So I need to go this way, 4, 5, then 6, right? If I count over here, 1, 2, 3, I need to go up because we're breaking this bond. 4, 5, and then 6, right? And so as far as the arrow pushing is concerned, this bond is breaking and you're forming a new bond here with 1. Here it's the same thing. Bond between 3 and 6 is breaking, forming a new bond at 1, right? And so let's draw both and you guys tell me which one we're actually following, right? And so here, what I do is, we reached number 6, right? So I'm gonna go ahead, I'm just gonna draw a 6-membered ring. Honestly, let me just, let me just draw it then. Okay. Cool. So on the numbering, it doesn't matter how you number. As far as my strategy, I'll just start numbering wherever. 1, 2, and then the same thing here. 6, right? Okay, so now let's start with the first scenario. 6 is making a new bond to 1. right? And so we met that criteria right here. That's the new bond. Who lost the bond? Who lost a bond in general? Basically, who's going to be the carbocation? Yeah, right. So 6 was originally bonded to 3. Now 6 took those electrons and made a new bond to 1. 3 is electron deficient because it lost electrons, plus charge here, right? Once we figure that out, we could transfer over the substituents. So just go each carbon at a time. On carbon 1, it has an ethyl. So I'm gonna go to carbon 1, I'm gonna put an ethyl. Carbon 2 is a CH2, so that's met. 3 is connected to 4 and connected to 2, and it's electron deficient, it's met. 4 has a methyl. 5 has CH2, which is good, and then 6 is connected to 5 and 1. Cool? Now let's go to the second one, right? So you guys tell me, where is everything gonna go? Who's the carbocation? Who's missing substituents? Anyone? So let's do this. Who's the carbocation?
I think it's still on 3.
Yeah, it is.
Pattern's still on 3.
Exactly. Yeah, it is still on 3, right? 3 lost its bond to 6 because 6 is now forming a new bond to 1. So still on 3. 6 has a methyl. 1 has an ethyl. So now look at the product and look at what we have. Which pathway are we following? Top or bottom? Yeah, the top, right? Because look, we have a methyl and ethyl, which are para, quote unquote, para to each other, whereas here they're right next to each other. So what does that mean? To make this, we need to break this bond right here. Okay, does that make sense, right? So you're always gonna have 2 options, but you need to figure out which option is actually correct. Okay, so, all right, so let me just start from here now. Remember that we want iodide to be on the same carbon as this methyl. So what are we gonna do?
Rearrange.
Yeah, exactly. We rearrange. So we're gonna have hydride shift. And right, so we have a hydride shift. So that means now we have our carbocation in the correct place. And now iodide will come in and form a new bond there. And so that is how you get to that product. Okay, so this. Okay, any questions? I hope that clears some stuff up with this, because I know it's difficult. All right, let's do the next one. Right, so this is different, right? Because we're opening the ring. I think in a way this is a little bit easier, honestly. All right, so what will be the first step? You disagree. Okay, well, let me show you. To draw this crap out. All right, so what will be the first step? Yeah, exactly. You protonate. Yeah. Right. So you protonate, and remember you're doing elimination, right? So keep that in mind. And so what do you just do? You just made a good leaving group, right? So if it leaves, right, we have 2 options from where it leaves, where it could leave from, right? If it leaves from this carbon, right? What type of carbocation will we form? Anyone know if it left? Yeah, exactly. We form a primary. So if it left, right, from this carbon, we would form a primary carbocation. If it left from this carbon, we form a secondary. So the correct way to do this is leading from the top because it forms a more stable carbocation. Like that, okay? So now let me show you guys a good trick for this. So whenever you leave, I guess, from a ring or when you're opening a ring, right, this bond is going away, right? So what do? You're just gonna erase this bond. And there, you're done, right? And just erase this arrow. And now this is neutral. And now what? Since it left from this carbon, positive charge, right? Cool. Okay, well, we need a pi bond, right? We need a pi bond, and so which beta proton is going to be eliminated? Think about the product, right? Yeah, exactly, the secondary, right? In this case, we can't take this one because it'll form a different product. And so I'll go ahead and show you why once we finish. Okay, so we're gonna take this one, not the other one, not this one. So TSO minus comes in. We'll do your elimination. And then you have this. Yeah, but the thing is, it's actually not a strong base, but the thing is, it can't do anything else. That's why it literally has no option. So this is one of your mineral acids that do dehydration. Since it's too big, it can't, what's it called? It can't substitute. And so it literally has nothing else it can do except eliminate. And so typically this is done under heat to promote elimination. Yeah, so this is one of your mineral acids. Okay, so now we need another pi bond, right? So what are we gonna do? We're gonna do this thing again, right? So we get TSOH, right? It's gonna protonate the alcohol. And so since this is what a primary alcohol, right? What mechanism are we gonna do? E1 or E2? Yeah, exactly, it's E2 only, right? Since we concerted. And so this is why we only took before when we were deciding between this one and this one, which is why we took this one. Because if we took this one, right, our product would be that. We would have two terminal alkenes. Whereas here we have an internal, right? Because in this case, the only option here is taking this guy, which forms a terminal alkene. Okay, so once again, TSO minus comes in. You do E2. And you form this. Right, so I'm just drawing in the same orientation. And this is that. Just fold it up a little bit. Okay. So, questions? And we're not going to be drawing any mechanisms, but I think it's good to understand the arrow pushing because it definitely helps understanding the reactions and what, like how you get the actual product. Okay. All right, so I'm gonna move on if there's no questions. Okay, so more mechanisms. All right, so you guys tell me, you guys walk me through. What's the first step for this guy? No one? Yeah, TS gets attacked by, oh, right. So here, oh, not that. Here, you would have to draw out the actual substrate. Let's do CO on this side. And so on this side is toluene. Right, so right, yeah, okay. Am I tripping or is that the structure? I feel like I'm missing something. Yes, that is, okay. All right, so now the first step is the oxygen atom attacks the sulfur, chlorine leaves, okay? And so after this, you could just abbreviate. So I'll put O, TS, the proton is here, right? And then positive charge. And so what happens next?
Pyridine deprotonates.
Nice. Yeah, pyridine's gonna come in and it's going to deprotonate. And that is it, right? That is it. So that is your final product. Okay, questions about this?
Hey, Jade.
Yeah, what's up?
Sorry, going back to the previous question here. So just wondering, would it always be made clear that there's an excess of that TSOH or whatever reactant?
Yeah, so in this case, since, well, we didn't technically use two because look, so we used one over here, right? And if we go over here, it was reformed, TS, and then takes its hydrogen, TSOH, and then so we use
Oh,
it
okay,
again here. If that makes sense. Yeah,
gotcha. Okay,
cool.
yep.
Yeah, but yeah, I think the only time you would need the specific amount of an acid is when you're doing the ether reactions. Like if an ether reacts with HX, then she'll say excess. If it doesn't say excess, then it's implied it's a 1-to-1 ratio. Okay. All right. So no questions on this, right? All right. So let's move on. All right. So you guys walk me through this. What's going to happen here?
Protonation.
Yep. Protonation. Okay, what happens after that?
It becomes a good living group, so
Mhm.
leaves.
Yeah, right. So here we're doing ROH with HX. So we know we're doing substitution. And so since it's secondary, we're doing SN1. Okay. So we are going through an SN1 type mechanism. And BR minus opposing SN2. Yeah, so it's not SN2, it's SN1, right? It's secondary. So you get this, right? And then what happens after this?
Hydride shift.
Nice. Okay, so I'm glad you caught that. So we have rearrangement. And so remember, there's always going to be before and after. So let's do before first, right? So before the shift, we have BR minus. It'll come in and attach itself, right? So that's one product. And so we have BR, right? So that's one product. And so, yeah, at this carbocation, right, we have a secondary, and right next to it, we have a tertiary carbon. So we'll have a hydride shift. Is one favorite or the other? That's a good question. Not entirely sure, but yeah, in this case, since the book doesn't really go over which one's favored for rearrangements, it's safe to assume that everything's formed equivalently, or there's no major or minor. So if there's a shift, right, you are expected to know that there are before products and after products. So like on the exam, you'll have to select all of them. She'll never ask you about major or minor. Okay. So did I draw this correctly?
No, it has to be plain on a plane.
Nice. Yeah. Right. So when we form a carbocation, remember this carbon is now sp2. So stereochem is lost, right? So now it becomes like a straight line. Now you could have Br minus coming in and attacking. And so that is how you form your other product. Okay. And there's no other rearrangement that's happening. Okay. So that's how you form both of these guys, right? So there's two products in this case. All right. Questions? Cool. All right, so what about here? What are we doing here in terms of the reaction?
It's just E2.
Nice. Yeah. So when we do ROH with Paco, it forces E2, right? So it only does E2. Cool. So the mechanism, 3 chlorines. So what's the first step?
The oxygen attacks phosphorus.
Nice. Yeah. So oxygen is going to come in and attack phosphorus. Any one of these chlorines is going to leave, right? And so you have OP, two proton here. So what happens after this?
The pyridine takes the hydrogen.
Nice, yeah. So pyridine is going to come in and deprotonate. And so you form your good leaving group, right? So now you could do your E2, your normal E2 mechanism, right? And so who is going to be acting as the eliminator? The base in this case. Who's going to be doing the actual elimination? Yeah, pyridine, right? Pyridine is a base, so it's going to be doing your elimination. And so remember beta protons, right? Alpha position, beta. There are no hydrogens here, beta, right? And then there's 2 here. So it's going to take one of them. I don't want to draw everything, so I'll just abbreviate. It'll come in and you'll do your 3 arrows for E2. And this is your only product. Right, that's your only product. Okay. Questions? Cool, cool. All right. Cool. All right, let's move on. All right, so what are the products, right? So let's do each step, right? So after 1, when you have an epoxide and you have this sodium methoxide, right? So after 1, what's gonna happen? Where is this guy gonna attack? Oh, God. He's gonna attack the least subbed or the most subbed? Yeah, the left sub side. Because remember, we're in basic conditions, right? Anytime you have an anion, you're automatically in basic conditions. Okay, I think acidic condition is going to be very obvious because you'll have natural acid. But yeah, it's going to attack the least sub, and then the ring pops open, right? So you form the new bond here, and that's where your nucleophile attaches, right? So that's after 1. What happens after 2? So when you react this thing with water, anyone? Okay, well, remember, so this is an anion, yeah. And so you use water as a protonation source, right? So you need to make this neutral. So you just put a proton on there, okay? And so now when this thing undergoes reaction with PBr3, what happens? Anyone? Yeah, you do SN2, but where? Where do you do SN2 at? What's going to be the reactive site? No one? OH, yeah. So remember that, what's it called? PBr3, it only reacts with alcohols, right? So we're only doing the reaction here. That's carbon, right? And ether is untouched. So it's SN2, so we replace basically OH with Br, right? Remember, it's SN2, so what's very special about SN2 reactions? What's going to happen in this?
The inversion, the stereochemical inversion.
Nice, yeah. So remember, SN2 is you backside attack, so you do inversion. So this becomes a wedge, okay? So that's that, right? Cool. All right, so we're gonna react this thing with mesylate chloride with pyridine, right? So what's gonna happen here?
Wait, for the one above, for the second product after the
Right.
step, was it OH or water? Oh, it was OH. Okay.
Yeah. Okay, so what's gonna happen with when this guy reacts with mesylate?
It attacks the O.
So it doesn't attack the O, it just you replace. So if you see MsCl, TfCl, TsCl, you replace a hydrogen with that abbreviation, right? So you just replace the hydrogen with, in this case, Ms. So OMS. That's it, right? Cool. And so now, remember what I told you, you would treat this as Rx, because why? This is a good leaving group. And so now you would go back to your chart from chapter 7 and 8, right? So if this thing reacts with KPH2 DNSO, what reaction are we doing?
SN2.
Yeah, exactly. And we're doing just SN2 because this is not a strong base, right? So we have this. Okay. Questions about this guy?
So we should treat every TFCl, TSCl, and this one as RX.
Exactly. Yeah, you treat it as RX because RX is like a something with a good leaving group on it, and this is a good leaving group. So yeah, anytime you see this, it's going to follow the same reactivity as chapter 7 and 8. So you could refer to your chart that way. Okay. Cool. So we have an example here, right? So you guys tell me, what reaction are we doing here?
Still SN2.
Yeah, exactly. We're still doing SN2, right? So this is primary. And we have a good nucleophile, but it's not basic. It's not a base. So it's just SN2. So since SN2, we invert. Okay. We react this with Br2. What happens with that? Nice. Yeah, it forms a disulfide, right? So what you do is you just take two of these and attach them together via the sulfur atoms, right? So I'll take this guy, I'll put a sulfur. So basically you form this and then take these R groups and put them on the sulfur, right? So and then same thing here. Right, that's all you do. You just you're combining two of these into one.
So anytime you have HS with any halide, then we get a disulfide.
Right, so it's going to be so it has to be an SH. So let's do RSH, and it's either there's two, there's Br2 or I2, and you get R S S You get a disulfide. Yeah. So you get diol specifically. Okay.
Yeah, thank you.
Yeah. All right. So next one, right? OH with the mineral acid. So what reaction mechanism are we going to follow here?
E2?
Close.
Oh, E1,
Yeah.
E1 secondary, my bad.
Yeah. No, you're good. You're good. Yeah, E1, right? So it's secondary. So we're going to do E1. Cool. So let's do this. I'll just talk my way through the mechanism. First step, protonation, right? Then remember it's E1, so we do carbocation formation. So it's going to leave first, right? So we get to this thing, right? And so now we look, right? Beta protons. So we have one here, we have one here. So we have two products. We have this guy, and we have this guy. So remember, anytime you form a carbocation, what do you have to worry about?
Rearrangement.
Yeah, rearrangement, right? So can this guy rearrange?
Yes.
Yes, it can, right? So we're going to do a hydride shift, right? We'll do a hydride shift and we'll get a completely new set of products. So now we have the carbocation here, right? And so we have two beta positions. We have two different ones, but in total we have three. We have this, and this, but this one and this one are the same. Okay, and so what happens here? We form two alkenes. We got this guy right here, plus this guy, but this one was already formed previously. So in total, we only have three different products because this one was already formed before, right? Questions about this? All right, cool. All right, so last one, right? So, oh my God. All right, so we're gonna react this alkyne with this. What's gonna happen here? Yeah, we do deprotonation, right? Because remember, this is a strong base, and so bases go after protons. This proton right here is relatively acidic, right? So we form the acetylide anion. So negative charge here, right? So that's after one. We take this guy and we react it with this epoxide, right? Oh, actually, and this was actually missing something as well. Forgot to mention it. And then there's a 3 water. Okay. Yeah, I forgot to mention that. So epoxide, right? So you got to think about, well, what conditions are we in? Are we in acidic conditions or basic conditions? Yeah, we're in basic, right? Anytime you have an anion, we're in basic conditions. So we're attacking this carbon right here, the lead sub, okay? So I can assure you, you will have an epoxide plus acetylide anion question on your exam because it's very, I guess at the beginning, it's difficult to draw it correctly, okay? Most people will and do it like this. Right, and this is wrong because all sorts of reasons, but it just looks wrong, right? What you do is you would, with epoxides, it's really easy to drop atoms, okay? So what you do is draw out your new bond, and on that bond, that's where you attach your nucleophile. So here, oh wait, there's stereochem as well. So since we're attacking this side, is this guy going to attach on a dash, or is it going to attach on a wedge? Yeah, it's going to attach on a wedge, right? Because remember, the ring is on a dash, so it's completely blocking that face. That means this guy has to come from the opposite face. So wedge, right? It's a come from the top. So draw out your new bond and then draw in the nucleophile. Right? And then everything on the other carbon stays the same because we didn't do any chemistry there. So you have O minus, and you have this wedge, right? And so you react this thing with water, and that'll give you your final product. Oops, all right. And so yeah, water serves as a proton source. So H. So that's that, right? Questions? All right, cool. All right, so last question, right? We're on the roadmap. So the NMR is for this box, right? Oh, this doesn't have a thing. Ooh, I forgot what it was. H. Give me a sec. Okay, so this has to be HCl. This is not that. Oh shit, yeah, my bad. I should look this over before I sent it out because I think when Professor Doherty made it, there was a few deficiencies. Yeah, my bad. I should have looked this over. So there is no arrow here. Okay, I think everything else works out. I hope. All right. Yeah, my bad. I should have looked this over. Okay, so let's do the NMR, right? Well, we got to figure out the formula, okay? Because she didn't give the formula in this case, so we got to figure it out. Well, what you do is you just count up everything, right? So 3, 4, 5, 6, 7, 8, 9, 10, 16. H16. Carbons 1, 2, 3, 4, 5, 6, 7, right? C7. And this actually has an oxygen atom. Well, how do you tell? Ooh, I think this had a lot of problems on it. Give me a sec. I should have checked the key before. All right. It's okay. On the test, you won't have to figure out the formula. She'll give it to you. It'll be the same exact format as last test in terms of like the roadmap. Same exact format. So she'll give you the formula. All right. So that's the formula, right? So what is du going to be? Anyone? Yeah. Yeah, it's 0. Right, so makes it a little bit easier, right? We don't have to worry about pi bonds or rings. Okay, so let's solve this thing, right? Is there, so we know we have an oxygen atom, right? Is there an OH in our structure? No. Okay, so how do you tell? That's the answer. Yeah, there is no OH, but how do you tell? Exactly. Yeah, there's no this on or NMR. So no OH. So that means that our only option in terms of like the functional group is an ether, right? Because that's the only other functional group that has an oxygen atom in it with no degrees of unsaturation. So it's safe to assume that we have ROR. Unless we have two R groups on either side, right? And which two signals are going to be directly coming off the oxygen atom in this case? Because remember, we have two sets. Yeah, exactly, right? We have two sets, and it's safe to assume we have two hydrogens on both sides. So we look to the furthest downfield. This guy and this guy are coming directly off our oxygen atom, right? So we have O, excuse me, we have O, we have CH3, and then here we have, what is it, CH, which is a hextet, right? So that solves a little bit of our structure, right? So let me just label everything A. So I mean, this is F, and that makes sense because it's super downfield and it's a singlet, and this is E, right? Cool. So where do you go from here, right? So I guess now we could just start normally. So we have a 6H, that's a doublet, right? So we have two methyls coming off of CH. Cool. Coming off a CH. As far as the CH, we don't know which one it is, or we do. CH, right? So we look, well, we have a CH here, we have a CH here. Which one would it be? Would it be D? Would it be E?
D.
It would be D, right? Because E is a hextet. This one is already a septet, right? So it can't be E. So I will label it. So this is A, and this is D. Cool. So D is a no net, right? So it has 8 neighbors. We already took care of 6. So what is its other neighbor?
Oh, the 2H, CH2.
Nice. Yeah, it's a CH2, right? Because it's a no net, 8 neighbors. We have 6 here, and so the remaining 2 is going to come from the CH2. And so we only have 1, so it's very convenient. So that's C. So let's keep going, right? It's a triplet. So that means 2 neighbors. So what is this guy's other neighbor?
the CH, that's E.
Exact. Yeah, CHE, right? That's our only other CH. So that is our structure, right? We're done. This actually no, not yet. My bad. CHO, CH3, and so we only have one thing left, which is our methyl, methyl B, to double it. So it's going to go right here, right? Because that's the only remaining spot. Okay. We good with the NMR? I think right now you guys should be getting pretty quick at it, hopefully. Okay, so as far as the answer, let me draw it out here. O, methyl, that is the structure. Okay, so let me copy it. So that's going to go right here. Okay, so I mean, we could go in any direction in this case. So let's go to the left. So it's reacting with HCl, right? So what's going to happen here? With an ether, right, we have two sides where we could actually use substitution. So we could put, our only two options are what? This or the other side. What's the answer?
The first one.
You sure? Right. So how do you tell, right? What are we gonna do? Well, look right here. Right. This is the only one that fits that formula. Does that make sense to everybody? Right. There's ambiguity, and it's very ambiguous, but you have to use the hints throughout the roadmap. So a formula is a hint. Right? Does that make sense?
Yeah,
Okay.
I was using the whatever it's called, Williamson stuff.
Oh, okay. So yeah, so that's different. That would be something totally different. Cool. So I guess let's go down, right? So we react this with sodium iodide. So we get what? We get just an SN2 reaction, right? We would replace it with iodide. And then if we go to the right, same thing. We'll replace it with bromine. Bromine. Okay. Cool. Let's go this way. So we react this with HI, right? And so we have, once again, two possibilities. If this reacts with HI, we can get this set of products. Or if we do it, the other way, we would get this. Cool, right? Does everyone see how we got that? Because there's always two ways to do this in terms of like cleaving an ether, right? Based off the formula, we know we have an oxygen atom, so it's either this or this. So that means what? Has to be this one, right? Okay, so let's move on, right? Pockle with OH does what? It does E2, right? In this case, we have two different beta protons. She did not specify which one, so it doesn't matter which one you put. Okay, you could put this guy. You put or you could put this guy. Right? It doesn't matter which one you put. You good so far?
Yep.
Cool. All right. So, working backwards, right? We have LDA with that. So we're doing elimination, right? But, well, what's going to go here? Look to the before reaction. It's going to be some TS molecule, right? So we would have, so let's do this to make it easier. Let's work backwards from here. What reacts with Sockle to get this? What type of functional group reacts with Sockle?
Alcohol.
Alcohol, nice. Yeah, so we just replace that with an alcohol, right? And if we go this way, well, an alcohol reacts with TSCl. Remember what I said, right? You just replace the abbreviation with the hydrogen, right? So you get TSO. That's right. So when this reacts with LDA, same thing. We have two beta spots, so either or can form. And so she didn't
Why is it
specify
13 carbons?
13 carbons. Yeah, so TSCl, right? You have to know
Oh,
the
but
structure.
then, okay, never mind.
Okay, cool. Yeah. Yeah, so the extra carbons, the sulfur, the extra oxygens, it comes in from the TS part. Cool. So that is your roadmap. Okay. Are there any questions about any of this stuff we just went over?
You make it look so easy.
Thank you. Here's a practice, right? And that's what I say, right? You just gotta do a shitload of these problems. And if you do a lot of these problems, there's really nothing that'll catch you off guard because there's only so many ways we could express this material in terms of questions, right? So work through the book problems, work through my worksheets, work through the problems Professor Doherty gives in class, right? If there's no questions, then
Oh, excuse me, Jeet. I got another quick one.
okay, what's up?
Yeah, sorry, it's not on this roadmap, but actually, I was just wondering on the formation or the synthesis of epoxides.
Okay.
Is it that you need to have like one of those, what are they called?
Halohydrin?
Yes.
Yes. Yeah, so let me do that real quick then. So if you have, oh my God, okay, so if you have a molecule with an OH and right next to it, you have a, what's it called? Halogen. And so the halogens we've been using, right? So Cl, I, Br, and you react it with, let's do strong base. Oh my God. Strong base, right? You will get an epoxide. So that is one way you can form an epoxide. Okay, and so how does this happen, right?
Is that just like a special case of like E2?
See that again?
So is that just like a special case of an E2 reaction?
So no, it's not an E2 reaction. This is SN2 like reaction. It's not E2 because we're not doing elimination, right? So your base is going to come in, right? It's going to deprotonate this hydrogen. These guys go back over here. And so you form this guy. Right? And so what do you have here? You have good nucleophile. You have good electrophile, right? Going back to chapter 7 and 8. And so what happens is it'll attack itself, right? This guy is going to attach itself right here. X leaves. And so what do? You just draw a line like that. So you could kind of see the triangle forming. And so that's how you get an epoxide.
Okay, okay, I got it. And doesn't matter what sort of a solvent you use?
No, generally there is no solvent used. It's just like if you have this and you have a strong base, then it'll form this. Generally, like there's no solvent that's shown. I don't know, it's weird. Okay.
Okay, great, thanks.
Yeah. All right. So if there's no more questions, I will see you guys on Wednesday. All right. I'll send out the key to this. I'll send out the key to the review sheet that I made yesterday. So work through those problems. All right. Good luck. Like I said, if you have any questions, feel free to email me.